Good day. My name is Luke Winsett, and this is my Milestone 2 submission. Okay, so for the first question, which ones are intensive versus extensive? Density, pressure, intensive, temperature, intensive, molecular weight, intensive, volume, mass, number of moles, extensive. Something that I found that was kind of interesting that helped me kind of understand like what's going on here is density, similar to like molecular weight and like density and things like that. The ratio between two extensive properties is an intensive property. So that's a pretty good way to kind of think about that. The next thing is okay. So the the thing to really focus on here is that this is an insulated cylinder, contains an ideal gas. The cylinder has a piston locked in place with the pins, and then once you take out the pins, it moves. So that means that because it's an insulated cylinder, that means the work cannot leave. I mean, in the form of heat is what I mean. Not no. The work can leave. That's the work is the only way that energy can leave the system. But the internal energy cannot change because it's an insulated system, so it can't lose like heat. Um, so that with work plus Q equals the change in internal energy. So any change in work is going to have to equal some sort of change in heat inside the system. So that means that the temperature will change. So the correct thing to say here was since the cylinder is insulated, the internal energy of the gas cannot change during the process. Okay, for the last one. So for the first thing we're supposed to look for is to calculate the number of moles in the sample of gas. I just instantly thought N equals KT over PV. That'll give us that. I had to do some. I almost messed up until I checked the units of everything. I think I got the right answer. But yeah, just KTPV. I can't remember. I think that there isn't too much to say here. Oh yeah, I assumed that room temperature was 300 Kelvin. It's 27 Celsius. That's one thing that I assumed. I also assumed something else, but I'll talk about that later. The next thing is the average spacing. So estimate the average spacing. So I didn't really thought about this one for a lot actually, but I think this is the right way to go about it. So if you think about the three mean path, that's basically the amount of like uh, it's the amount of distance that um, a molecule is going to travel until it bumps into something. So while it could like bump into it's going to be like bumping into like it could bump into here or bump into like anywhere, you know. So it's like it's really kind of like not exact, but I guess that's kind of like you can't really be exact with this sort of thing. So the actual like straight up distance between like average distance, I guess this is the best way to do it. I Because getting this exactly is going to be impossible. So use the free mean path, and that's square root 2 pi d over the moles per volume. This is the unit density. And I almost messed up here as well, but I think I got it right answer as well. 5.4366 e to the minus 15, and that is in meters. Okay, number 3 is estimate the average speed using the Maxwell-Boltzmann distribution. So Maxwell-Boltzmann, you can do a lot of math. They give us this equation right here. This because it gives us v average. In the middle in the distribution, it'll be pretty sure it's this one right here. This is the root mean squared, and this one right here is the peak, the PV, or I'll look it up later. This is P average. I'll include it. I'll write it down when I submit it. So this is so just convert from N to N2, O to O2 because it's in the gas form. And then you just get you plug in the equations, RT, T 300 again, um, R is the ideal gas constant, and then I got the percent composition of N and O2 in a just standard air. There was like some argon and other things like that. It only said N2 and O2, so I just assumed that argon wouldn't be a lot of the total amount, so I just kind of left that out. So that was the last thing that I assumed. So the O2, wait, okay, so yeah, so the O2 value is this, N2 value is this for the speed, and then what you do is you multiply, I'm pretty sure I did this right, so you do just it's just a percent, right? So you just multiply the speed by the percent of N, and then O by the percent of O, and then you just add them together. You don't need it, and that'll just give you the average of between those two, because it's you're just multiplying it by a percent, and I think you don't need to divide it by two. Pretty sure you don't need to divide it by two. But yeah, that's that. And then okay, so then this last one is okay. So suppose the ideal gas were scaled. Okay, so yeah, this is just a ratio between the atoms and the diameter of the tennis ball. I just used that ratio to get me the number of liters, convert that to meters, meters cubed to convert that to meters. Here, same ratio, I just took the V average as well for V average to D equals diameter tennis ball to, well, I just used that and then multiplied diameter tennis balls times the velocity over the diameter of the atom is that it will equal to y. Y is equal to this, and then I just kind of had some comparisons here. This is really, really fast compared to like a bullet or a rocket. That's really fast. All right, that's my submission for milestone 2, and yeah, thanks for watching.